Hello and welcome. In this video, we are going to perform the lab called Planck's constant, the purpose of which is to experimentally determine Planck's constant. Let's start by reading the introduction here. The energy lost by a single electron that passes through a light-emitting diode or an LED is converted into the energy of a photon. Since LEDs emit light of a specific wavelength, the minimum voltage required to emit a photon can be used to determine the energy of the photon. Knowing the energy and the wavelength of a photon, one can determine Planck's constant. All right, we have a couple of equations here. One of them is the energy of a photon, the energy of a photon, all right, derived by Max Planck, a German scientist. The h in the equation is what's called Planck's constant. The F represents the frequency of the light of the photon. And then E times V is a way to measure energy, And that would be the charge of the electron times the voltage needed to light the light bulb or light the LED. The other equation is just a wave equation for light, c being the speed of light, f the frequency, and lambda the wavelength. So we can use both of these equations to try to derive Planck's constant. The circuit that we need is shown by this diagram. We need two components. We need an LED and a small resistor in series with it. We need a variable power supply that we can change the voltage to, and then we'll also need a voltmeter to measure the voltage across the LED. Now, what would this look like? Here's a circuit board that contains the components we need. We have our resistor, 330 ohms, and we have a series of different LEDs of different color, blue, green, yellow, red, and this one is infrared. And what we're going to do is hook up each one of them in series with the resistor one at a time, measure the voltage across this to just barely light the light. Okay, let's take a look at the procedure. Number 1 says, turn the power supply to 0. Connect the circuit as shown, then slowly turn up the voltage until the red LED just lights. Record the voltage. All right, let's take a look at what this looks like. Here is our variable power supply that we can set to various voltages, and we're going to do each one of these light bulbs one at a time. All right, so first we shall connect to the resistor and then through. Let's first do the red one here. So I'm going to hook up to the red LED, and then I'm going to slowly turn up the power supply until the light bulb just lights. All right, can see how it lights there? Now notice this, that as I'm turning up the voltage, it doesn't light right away. All right, 0.891. At some point here, all of a sudden, the light bulb lights, the LED lights. So there's a minimum voltage required to make that light bulb light. Now, what happens inside of an LED is that there's two pieces of metal, and electrons have to jump from one to the other. And in order for that to happen, the electrons have to have a certain amount of voltage. And when they jump from one piece of metal to the other, they jump from a high energy level to something that's lower in energy level, and then the difference is given off in the form of light. So that energy of that photon given off is equal to that difference in the energy level, and the voltage is what's going to determine whether the electron can jump across the gap or not. So what we need to do here then is slowly turn this up and record that voltage across the LED when the light bulb just lights. All right, so we'll have to kind of look at it real close and see when we first see the light bulb light. All right, almost there. 1.5. Now, it's very dim. It's very, very dim. All right, I want to back it off a little bit. And the light bulb just goes out. So that minimum voltage needed to light the red LED was 5 volt, 1.5 volts on this. But remember, we got a resistor in series, so it's a voltage divider. So what we'll need then is a separate voltmeter to actually measure the voltage across the LED. So we'll use this as our voltmeter to measure the voltage across the LED. So I have the set to measure volts, and I'm going to put it across the LED, and we get 1.49 volts. All right, so we can record that in our data table. Okay, that was for the red LED. All right, let's do all of the voltages first, then we'll come back and measure the wavelength. The infrared one is going to require a little bit different practice, so we'll say that one toward the end. Next, we'll light the yellow ones. I'm going to move this over to the yellow LED, and notice that it does not light just yet, so I'm going to back down, and I'm going to slowly increase until the yellow one just lights. All right, looks like right about there. Right about there. All right, and with the voltmeter, measure the voltage across it. .68. 1.68. We shall record that. For the yellow one, 1.68. Next, the green one. Moving over to the green one and turning up until it just barely lights. Notice it's taking a little more voltage now each time to light these. All right, that one is right about there. Measuring with the voltmeter, 2.04. 2.04. Then the blue one. All right, this one will turn up until it just lights. Oh, there it is. There it is. Backing down. Just lights right about there. All right, measuring the volts across it. 2.40. 2.40 for the blue one. All right, now, how about that infrared one? How are we going to do that? Because infrared is invisible. You can't see infrared. Okay, let's switch over to the infrared LED. And I'm going to turn the power supply to 3 volts, which is sufficient amount to actually light an infrared LED. All right? But looking at it, we cannot see, and nor can the camera of this iPad see that that thing is lit. So how are we going to know if it is lit? All right, what we can do is use an Android phone, which can actually see infrared. Look at that light right there. That light is lit. All right, with that camera we can't see anything. Through this camera we can actually see a little purple light. Now to the camera, the color of it is purple. All right, and that's just the circuitry converting it into something that our eyes can see. All right. Okay, let's turn this down so that light bulb goes out. All right, now we're going to slowly turn it up until the light bulb just lights, and the camera on the phone will be able to detect it. There it is. All right, there's our minimum right there. All right, next what we need to do is measure the voltage using the voltmeter. All right, the voltage on the red LED, or the infrared LED, 1.09. All right, we can record that. 1.09. Next then, we need to use the spectroscope to measure the wavelength of the light emitted from each diode. Now, how are we going to get the wavelength? We're going to use a spectroscope. A spectroscope has a little hole in here and light shines in, goes through this diffraction grating, and then there's a scale. We line it up. We're going to use this one, which is mounted to a little tripod. We're going to set that up next to our light. First, we're going to use a white light, so see if we can capture a full rainbow. All right, we're going to line that up there. We need something to illuminate the scale. All right, to capture it, we're going to use the camera on the phone. Bring that right up to it, and there it is, full rainbow. Snap a picture, and there we have it. Spectrum of a white LED. Then we got to do that with each one of our bulbs. So starting with the red, all right, there's our red. Looking for yellow. Looking for the green. All right. There's our blue. We'll download those. And here are the pictures from the spectroscopes. Next then, we have to measure the wavelengths. So looking at the red one, the brightest spot looks to be right about there. Let's call that 615. Now that's for the red, so I'm going to write 615. That's in nanometers, so I'm going to write that as 615 times 10 to the minus 9. And then for the yellow one, the bright spot right in the middle of yellow, let's call that 530 for yellow. 530 times 10 to the minus 9 for meters. And then yellow green. Green looks to be right at about 515. 515 times 10 to the minus 9. And the blue one, let's see, I think the blue one looks to be right about there. We'll say let's go with 460. 460 nanometers. Now, how about the infrared? We can't see that or measure that one. For the infrared, what we'll have to do is go to the website and get the spec sheet. And that will tell us what the wavelength is. It says peak emission wavelength 940 nanometers. So we'll write that in, 940 nanometers for infrared. And that would be times 10 to the minus 9. All right, so we've got our wavelengths and our voltages. Next then, we have to do some calculations. Number 1 says to calculate the frequency of the photons. Now, we know that c is the speed of light, 3 times 10 to the 8. And we have the wavelength. So to calculate the frequency, we'd have to do F equals C divided by lambda. F equals C divided by lambda. So we're going to use C and these wavelengths there, and we're going to calculate the frequency. For the infrared, we're going to have 3 times 10 to the 8, 3 times 10 to the 8 meters per second, divided by that wavelength of 940 times 10 to the minus 9 meters, and that gives us 3.2 times 10 to the 14th. A very high frequency, but light has a very high frequency. Now, to calculate the energy of the photon, we have energy equals E times V. E is the charge of an electron, and V is the voltage. Now, since volts are actually joules per coulomb, if we take the charge of the electron, 1.6 times 10 to the minus 19 coulombs, times the volts, which is 1.09 for the IR, joules per coulomb, or volt, we will get 1.7 times 10 to the minus 19. Now, a single photon does not have a lot of energy. Then we have to do similar calculations for the red, yellow, green, and the blue. And we will get the following data. The rest of this is for you to work on. In the analysis, you need to create an Excel graph of energy versus frequency. Energy versus frequency. It should give you a straight line. Then you want to fit it with a trend line to find the slope of it. Remember that a photon has energy is equal to h, Planck's constant, times the frequency. So the slope of this graph is going to be Planck's constant. Planck's constant. Now, we didn't tell you what that is, so you'll have to find out the theoretical value by doing a quick little Google search to find out what it is. Then you'll compare that to the slope of your graph, find the percent error. For this extension, you're just going to take the info that's in the chart here and fill out the rest of the chart. For these two, you got the relationship of C equals F times lambda, and we know what C is. For these two here, the relationship is that a electron volt, a way to measure energy, is equal to 1.6 times 10 to the minus 19 joules. All right, because electrons are measured in coulombs and volts are measured in joules per coulomb. So if we take the charge of an electron times 1 volt, we end up with 1.6 times 10 to the minus 19 joules. That's what an electron volt is. Sometimes in particle physics and modern physics, we use electron volts to measure energy rather than joules. All right. For the last question, a green laser pointer like this one, careful with that could blind you, produces 530 nanometers of light with a power rating of 1.0 milliwatts. How many photons does a laser produce each second? Now remember, we determined that the energy of a photon is quite small, and this one is only putting out 10 or 1.0 milliwatts. So we'll have to figure out how many joules one photon is if it has a wavelength of 530 nanometers. Then we can figure out how many photons per second the laser produces. All right, thanks for watching.